So getting started. Welcome to ski school. Can everybody see, or should I sit down? Or? Very good. Okay, so how many of you have heard of this, of combinatorial logic or SKI calculus? Wow. And how many of you are sort of wondering what it's about? Or how many don't care at all? Okay. Yeah. Okay. Okay, so what this is basically mathematician Moses Schoenfinkel and later developed by Haskell, Curry, of whose name has been lent to both Haskell and currying. Even though Schoenfinkel sort of invented currying.
No one wants to say that.
Yeah, no one wants to say Schoenfinkeling. So.
It's going to be the name of the next great functional programming language.
Yeah. How many have heard of the lambda calculus? Okay. And I assume since most of you have seen some functional programming, you're comfortable with things like this. This Haskell notation. So this is lambda x. So we're taking x as a parameter, and then we're taking y as a second parameter, and then returning x. But this is what's called a curried form. So we have x. We're taking x as an argument, returning a function that takes y as an argument, and then returning x. So that's a function that in Haskell we call const. It takes two parameters and returns the first one, ignoring the second. So const is a combinator. And what is a combinator? A combinator is a function that operates on functions and returns functions. So it's what you might have heard called higher order programming. And it enables kind of programming called point-free style. Points are these parameters. So when you define things with lambda, you're defining a parameter, and those are also called points. So point-free means if you use const instead of this, then you don't have to write the lambdas. Now, that's not necessarily always an easier way to write things.
Can I interrupt?
Yeah, go ahead.
Is this what drives the @pl command for lambda-bot?
I don't know lambda-bot.
It sits in pound Haskell, and it will point-freeify your code for you. Oh, it could. I don't know. That's interesting. It probably does a simpler transformation. It probably doesn't use these combinators. So, yeah, Schoenfinkel and Curry, they found that you could actually write all programs. Any program you could possibly write, you could write with just these three combinators, S, K, and I. And we'll see later on how we can reduce that even further. But so K is const. It's this function that we're talking about here. And that's pretty easy to wrap your head around. I is the identity function. This is just an example where I'm applying the const function to 1 or 2, so it returns 1. And lambda has made its way into Ruby, Python, and C#, as we saw. I'll get down to I in a second. So here's a problem with reasoning about the lambda calculus. What happens when you have a function that takes x as a parameter, then takes x as a second parameter, and returns x? What does the second x, or what does the third x refer to? Is that the first x or the second x, or are they all the same x? So, yeah. So it turns out that it's the second x because that's the rule, the way we define it. But just this kind of stuff makes it harder to do mathematical proofs and reason about it. So they thought, although actually this combinatorial logic was invented before lambda calculus, so I can't quite say that the motivation was that lambda calculus was annoying, but they had, I don't know, I can't completely explain the motivation. But, what was that? Yeah, you can do an alpha substitution. Yeah, alpha renaming or whatever, rename the variables.
Yeah, but that's like an extra step that makes working with lambda calculus proofs awkward. These three functions, sk and I, can be used as a basis for all computation. I is the identity function, and all my parameters here, it says this Haskell notation as well. This means, well, except that I'm using a capital I and you can't use a capital letter for the name of the function, but for clarity in this presentation, for identifying our combinators, I'm going to use capital letters for those. So this function I, when applied to argument f, returns f, identity function. And then here's our const function. It takes f and g and returns f. And the reason I've called these things f and g is because in combinatorial logic, everything's a function, which means it's actually it's completely untyped. So if you thought, oh, Haskell has really strong typing and Ruby, has pretty good typing, but it's dynamic typing. Well, combinatorial logic has no types at all. I mean, everything is the same type. Yeah.
Are there like a type combinator calculuses?
Yeah, there's like typed lambda calculus, and there's probably typed combinator calculus. I haven't looked into that, but. Well, one of the problems you'll see when I run this in Haskell is Haskell trying to infer the types on this, like it explodes its brain. So, so S is the third combinator, and that's a little bit trickier to wrap your head around, but it takes three parameters, curried form, and then it applies the first parameter to the third parameter, applies the second parameter to the third parameter, and then applies that to that. So you're like, well, that's kind of weird.
There's an easy way to think of that.
What is the result? Sorry.
Yeah. What was your
You can think of that
suggestion?
What S is doing, it's applying f to g. Like, just ignore the h.
Yeah.
It's really just applying one function to another
Right.
function, so it's kind of application. But everybody is parameterized by h, so
Yep.
it just distributes h to everybody. So this is kind of a distributing combinator,
Right.
which is really good for passing information to many combinations.
Right.
Yeah,
That's what I said in this paragraph down here. That's right.
It's as if
So-
H is an environment.
Right. You can think of h as this parameter that's. So you can imagine. Remember, well, you're going to talk about functional reactive programming. We talked a little bit about it before. But if you imagine that you have some function. Imagine you have some function that changes over time. It's plus 1, and then becomes plus 2, and becomes plus 3, and it's like changing over time. And then you have a value that changes over time. So the number 5 maybe becomes 10, and then becomes 20. So if you want to take a snapshot in time of the changing function, and also a snapshot of the changing value, and then apply that function at that instant to that value to get a result. That's the concept of both the function and the parameter, function and its argument being parameterized. However, h isn't a time, it's another function.
I think an easier way for me to read that is to mentally put parens around the f and h on the right-hand side.
Yeah, you can also think of it that way, right? Because there's three arguments. Yeah, you can write it that way.
Since this is
Mhm.
untyped,
Yeah.
since this is untyped, that means that the result of applying h or applying f to h is also a function.
Yep, everything's a function. And you can apply things as many times as you want. You can apply any function to any function. So how the heck do you compute things with this if there's no types? There's no numbers, there's no strings, there's no booleans, no nothing. Well, if you think about computers and the way they're put together, you have everything's represented in binary anyway. All that stuff is untyped. You just have a bunch of bytes of zeros and ones. And the typing is really just a way of interpreting. It's what your expectation is. If I look at 32 bits and I expect it to be an integer, then it's an integer. So you can apply that same kind of thing here with the combinatorial logic or in lambda calculus. And you can write a function that generates something that's like some representation of a number. So how can we represent? Well, we'll get on in a bit how you can represent numbers with this. So this is just an aside. It turns out that this S combinator is in the standard Haskell libraries. It's this angle bracket star right angle bracket, but only a particular instance of that function. So you can pull lots of tricks with S. But it may seem a little bit weird that we have like an extra h in there. What if we wanted to define this combinator like flip in Haskell? Well, flip takes a function and it reverses its expectation of its arguments. So flip fxy is fyx. Well, turns out Haskell Curry called this C. Why isn't I saying B there?
Okay, that was going to be my question.
That's because they're two different functions. So C is this flip combinator. C is his name for flip. B is a different function, which is turns out to be composition. So if you apply B to F, G, and H, it's taking these three arguments F, G, and H. That X should be an H, sorry. So it applies G to H, and then it applies F to that, which turns out to be function composition. And it's essentially the same as composing F with G.
So what does flip look like using SKI?
Unfortunately, I don't think I have that example written out in here. We'll see some other cool stuff.
Jeez, me with the flip.
I know. Okay, Schoenfinkel called them T and Z, and he showed how you could write those in terms of S and K, but I'm not showing you right now. So let's fool around with this and try a sample reduction. SIKS, what happens when you do that? Well, and it turns out to get this stuff straight, you just have to do it over and over and over again. I kept messing it up and wondering why I was getting the wrong answers, but it just takes practice. So SIKS, you take, that means we can apply I to S and K to S. So here's our K applied to S. I don't need to parenthesize the left-hand side because the parens on that side are implicit. So what is I applied to S? It's just S. So it reduces to this. And we can't reduce it any further. And then we have SK. That turns out to be pretty interesting. So SK means apply K to K, and then also apply S to K separately, and then apply those to each other. And what happens when we apply K to K and something else? Well, it ignores this term, and we just get K. Okay, so this is all about how can we compute with these things, and how can we encode numbers. Our hardware is using some kind of binary representation. In set theory, you don't have to remember this, but in set theory, a natural number is defined as the set of all the natural numbers less than itself. So these square brackets I'm putting around things mean this interpreted as. The interpretation of this is. And then there's another kind of numeral called Peano numerals. And those are a very structured type. So you think, well, sometimes I work with structured data types, but then sometimes I work with numbers, and those are just a different thing. Well, it's possible to treat numbers as a structured data type. So in Haskell, we define a structured data type like this. We have a data declaration, and we say our number is either 0 or the successor of another number. So nat being natural number. So 1 is the successor of 0, 2 is the successor of 0, and so on. So 3 looks like that. Suck, 0. So those will come in handy in a bit. Church numerals are the way that Alonzo Church, who devised the lambda calculus, came up with to represent numbers with using just functions. So there's a relationship. They're closely related to the Peano numerals. The idea is 0 is represented as a function that takes two functions. I'm going to call them lowercase s and z. Don't confuse this s with the capital S I was using for the combinator. This is supposed to represent some kind of successor function. It's supposed to represent some 0 function. So given a successor function and a 0 function, I return the 0 function, or whatever thing I'm given. So 1, and you give it successor function and a representation of 0, and it applies the successor to 0, and so forth. So it turns out that if we feed the constructors suck and 0 into this, we get exactly back the Peano numerals. Does that make any sense? Or yeah.
Yes. I
Okay.
was off in my own little world, so I
Okay. That's okay. Yeah. So here it is written out. So 3 suck 0 is suck of suck of suck 0, which is the Peano numeral. Yeah.
What were the numerals before with the sets?
That's not going to be relevant from here on. I just showed that as a contrasting example, but I'll post this, and if you're interested, you can look at it later.
I'm sorry, I'm looking at the way your cursors now. The 0 SZ equals Z.
So this function, this church numeral 0, takes two parameters and it returns the second parameter. So if we feed in the constructor suck here and the constructor,
what the syntax is supposed to be like. What is more of these things?
It means that you apply the parameter to the function s 0 times, so you just get the 0 back.
So is 0 a function, or is it just like a label on that line?
Everything's a function, so yeah.
those are all functions. Well, S and Z don't have to be functions. Yeah, go ahead.
Think about it this way. This is a function that takes a lambda and a value. And the number is how many times should we apply the function to the value. So the value is z here and the function is s.
Okay, so you just throw away the function.
So
you
it
get
says
the
when
value.
it's 0,
Okay,
we
okay.
don't apply the function, we just give you the value.
Right.
Once
That makes sense.
Yeah. It's easiest to think of S as a function here and Z as just a constant
As it turns
value.
out, in the lambda calculus, all you have is functions. You don't have any values. So if all you have is functions, all you can do is apply them. And you go, well, let's go to the numbers with how many times you're going to apply them.
Yes.
Right, but it turns out when we represent, when we write this stuff, in Haskell or in Scheme or some other language, we do have other types. So even though we create these church numerals that are just functions that apply things to functions, we can also feed them things that aren't functions. We can feed them things like this 0, this capital Z 0 value. And that lets us kind of see what's going on. I could show you right here, we could go to the Haskell code because I have this defined in Haskell. I have some SKI stuff, and I have church numerals defined down here. And I've defined them in terms of SK and I, actually. So I'm skipping ahead a little bit there, but make that bigger. And HCI, SKI. If I say 1, suck 0, oh, we forgot 0. No, I didn't define 3.
You're like the Valve Corporation.
Yeah, there's no 3. So here's a neat trick. Instead of putting in suck and 0, what if I want to get out our usual representation of integers? I can put in this function +1 and the value 0, and what that does is apply +1 3 times to 0 and gives us 3. So, nerd note, if you know anything about catamorphisms, these church numerals are a catamorphism of the natural numbers that have been applied to a number, but are waiting for an algebra. So normally catamorphisms are applied to an algebra first and then to a value. But Anyway, don't worry about that. Don't worry about that. That's just a total aside for people who
Isomorphism is just
know what that
a
is.
fancy way of saying a fold function.
It's a fold. Yeah, it's a generalized kind of fold. Yeah. Right. So these are purely functions, don't rely on data types, so we can use them to represent the SKI calculus. Now, how do we write this in terms of these combinators? So 0 is turns out is ki. So what happens when we write ki as z? The k ignores the s, so we get iz, which reduces to z. So that's what we want. 1 turns out to be just the identity function, because we want to apply the successor function to 0. 2 is a lot trickier, and one way to do this, turns out there's a way to like systematically translate stuff from lambda calculus into these combinators. But I sat down and like tried to wrap my head around it, and I'm not sure how much time I want to spend on this, but I think I came up with a pretty good explanation, pretty good derivation for this. So we want to repeat this successor function, and the S combinator is the only thing that's going to let us repeat things, because see how this H shows up twice? So that seems like a good start. So what we want to do is we want to repeat this successor function argument S, but we also want to apply it. We also want to compose it with itself, because we want S composed with S applied to Z. So there's 2 things we need. One is we need to represent function composition, and the other is we need to be able to replicate arguments. So I'm going to go over this a little bit fast, and don't worry if you don't follow it all. I'm going to post this, and you can look it over later. So dot represents function composition in Haskell, and if we were to define it, you could define it like this: f dot g applied to h is f applied to g applied to h. Is anybody having trouble with that? Okay. So it's like it's shifting the parenthesization. So g and h they were separate arguments, and now they become parenthesized. Well, this S combinator has some parentheses on the right, so that's encouraging. But there's this problematic H on the left, which we don't really want there. I want F applied to G applied to H, but I don't want that other H in there, so how can I get rid of it? Well, K gets rid of things, right? It gets rid of like the second argument, so maybe we can use that. So K, let's see, what happens if we do KFH applied to G of H? Well, that will get rid of that H, right? And that's what we want. But how are we going to get to that? How are we going to get that formula? So is it just KS? Is that what we write? Well, what happens if we apply KS to F, G, and H? That cancels out the F, and then we get S, G, H. No, that's not what we want. Do we want SK? Well, what does that do? That applies F to G in the parentheses, and applies K to G. Puts it over here. No, that doesn't do what we want. It's not applying the F to the G. It's not even getting to this H. This other H is just sitting out there. It's not even affected by this S. So that's not right. Now we need the K to be applied first. We need it to work like this, like K applied to F. So if we had S applied to this grouping of k applied to f, and then to g and h, then we would have, let's see, so that's kf applied to h over here, and then and then g applied to h over here. So this k cancels out this h, and we get f of g of h. So that's what we want, but how do we get this f like inside these parentheses? It won't work without those parentheses. So we can make the k eat the h, but we can't get the f inside the parentheses. Well, you know what we need? We need this dot operator, because then if we compose s with k, then we get s applied to k of f, right? Oh, so that'd be great, but wait a second, isn't that what we're trying to construct, is this dot operator? So, well, wait a second, though. Turns out the problem with constructing this dot for a composition is that we don't know what the two things are we're composing together. Turns out if we know exactly what terms we're composing together, there's a shortcut to getting it. So, look at this. So suppose we have these arbitrary expressions E1 and E2, and if you compare this to that, you see it looks very similar. And what happens here is we get k E1 applied to f and E2 applied to f. The k cancels out the f, and we get E1 applied to E2 applied to f. So that works great, and the reason that we were having a problem before is because we wanted f in here, and we couldn't just stick it in there. But this time we want k in there. We couldn't just stick like some arbitrary parameter in there, but we can stick a known combinator or a known combinatory expression in there. So if we want to compose s with k, we can use this trick, and we put an s here and a k here. And then we'll end up with that. See? So when we substitute those in, we get this. And then we have ks applied to f and k applied to f, and they're left over gh. The k cancels out the f. We get so now this s is moved over here. Then to apply this s, we apply kf to h and g to h. This k cancels out that h, and we have f of g of h. Voila, that's exactly what we want. So now we have this entire left-hand side is all just pure combinators. There's none of these parameters in there. So this combination s, and then parenthesized ks and k, is exactly what does function composition. Okay. So what about the replicating the arguments on the right-hand side? Because that's the other thing we need to do to create the number 2. Well, s again looks like a promising thing. What if this g were an I? Then we'd have FHH. So we want to replicate some argument. That looks like the way to go. We put in I for g, but the problem is we can't just put in something for g without putting in something for f. You can only substitute predefined parameters starting on the left, because all the parameters to come are going to be on the right. So, but wait, what if f were the composition operator? What if we put in the composition operator for f? Then what happens? That seems promising, because then if we had a composition function here, and we had I here, then it would look like this. And we have s and the composition operator. This means the parentheses around it mean we're isolating that function, so it's no longer infix. So that means this composition function applied to h, and I applied to h, and I applied to h is just h. So this is the composition of h with h. And that's exactly what we're looking for. We're trying to take that suck function and apply it to itself. So now all we need to do is expand that composition function into our definition. This is what we wrote is the composition function, and we fill that into here, and we get this. And when you process through all these steps, you end up with s of z. So that's so that whole string is the Church numeral 2. Now that looks really complicated. But fortunately, it turns out that if you just apply that magic string again, you get 3. And you apply that again, you get 4, and so on. So over the hump, and after that, it's easy constructing all the rest of the Church numerals. So you may have noticed it's pretty verbose compared to the lambda calculus. It's because we have fewer symbols, so you end up having to make things longer. So testing it out, we did that with the Haskell code. Here's some other magical incantations. This turns out to be reverse application.
So is this flip?
No, it's flip of dot.
Flip of compose?
Yeah, it's flip compose. This one.
Not flip apply.
No. Flip of compose takes two instead of taking a function and an argument, applying the function to argument, it takes the argument and then the function and then applies the function to the argument. So it's, yeah. So that's what this reverse application is. Self-application, SII, turns out apply that to F, and it applies F to itself. Here's a crazy infinite loop. SII applied to SII. It reduces to this intermediate step, and then it reduces back to itself. So it just keeps going forever. And that's demonstrating the Turing completeness. Yeah, and I'm not going to delve into the Y Combinator today, but if you want to see what it looks like, this is the Y Combinator written in SKI calculus. And we can use that to compose with special open recursive functions that we can use this to generate any recursive function we want, like factorial or so. Okay. So it's kind of a pain to guess all these things. I mean, it was fun, but wouldn't it be nice if there were a way to like automatically, like mechanically generate the appropriate SKI terms? And it turns out there is. I just put a link here. I'm not going to go into it unless we have time, and probably running out of time. So turns out S turns out to be really useful in that. And if you look at that link and the transformation, S may now make even more sense because it turns out to be really useful in translating a particular lambda calculus term or form. So it turns out we can make things even smaller because SKK is equivalent to I. So if you apply, reducing our S, we have K applied to F, and this K applied to F. This K ignores the second term, which gives us F. So that's exactly the same as I. And since the second term was ignored, it turns out we can put anything we want here. It can be K, it can be S, it can be I. It doesn't matter what that term is. So we don't really need SK and I, we just need S and K, right? Well, turns out you could do it all with just one combinator. Chris Barker invented a combinator called Iota, which can be used to generate S and K. So it's sort of like how you can have a square root of -1, and then when you multiply it by itself, you get -1. And you multiply that by the square root of -1, and you get negative square root of -1, and it kind of rotates around these axes. So iota applied to itself gives you I, and I'm going to call iota x here just for ease of reading. So x applied to x is I. And here's the definition of the iota combinator, or x. All it does is it takes a function and it feeds it the arguments s and k. That's it. So let's see what happens if we start writing a bunch of s's and k's after each other. So sk reduces down to k, and we saw that before, actually. But let's keep going. What happens if we take k and we feed s and k as arguments to it? Well, that reduces to s. So you see, this is the same as applying iota to k, and we get s.
Are you saying all of these can be expressed in terms of each other?
Well, yes. I mean, there's sets of combinators that are called a basis. And so s and k form a sufficient basis for describing all functions in the lambda calculus. Iota also forms a basis all by itself.
Okay.
So using iota, you can express s
iota
and
is equal to sk is equal to ski is equal to the lambda calculus?
yes,
Okay.
exactly. Yeah, iota is equivalent in power to ski, which is equivalent to sk, which is equivalent to the lambda calculus. So what happens when we take s and we feed it s and k? Well, we get ssk, which is irreducible. Let's add sk again at the end. Well, that reduces to sk and parenthesized ksk. And remember that form? Remember we said skk is equal to sks is equal to sk anything is equal to I. So this is I. So what happens is we have this 5-step rotation. You apply x to x, you get I. You apply x to I, you get sk. X to sk, you get k. X to k, you get s. X to s, you get ssk. And apply x to that, you get back to I. That, by the way, that little rotation, I didn't read that anywhere. I figured that out the other day. I'm sure that the guy who came up with this figured it out, but I didn't see it written anywhere.
It's always fun when you impress yourself.
Yeah, I was pretty excited to figure that out. So what is iota and ski? Well, using the mechanical reduction steps that I didn't show you, it comes out to this. And here's a proof that it works by reducing this term down. Okay, one last thing is that Chris Barker said, well, we don't like all these parentheses because then you have to group things together, and I want something that parses just completely linearly. And these parentheses, constructing a tree, that's like too complicated to reason about. So he came up with Jot. And Jot has no parentheses, but it has 2 combinators. So he had to make a trade-off. We have 2 combinators, no parens. And just to confuse matters, he called these combinators 1 and 0. Well, the clever idea is that then you can write any string of 1s and 0s, and it represents some function in the lambda calculus. And then every function in the lambda calculus can be represented by some string of 1s and 0s. It's not a one-to-one correspondence, but yeah. And so some people actually have used this to try to figure out what percentage of programs terminate. Of course, it's totally biased by your encoding. And okay, so the 0 combinator is iota. So we've just seen that. The 1 combinator is function composition. It's our dot. So just using iota and dot, you can chain them all together. And just for fun, the empty string is defined to be I, the identity function. So here's the encoding for the k combinator in Jot. It's 11100. And we can reduce this step by step. So if this 0 represents iota, it means add s and k as arguments. So here's our s and k as arguments. And the next 0 also adds another s and k. This 1 puts parentheses around these next 2 because it's composition, so it's grouping these parameters. And there's another 1, so we're adding another parameter to the group. And another 1, we're adding another parameter to the group. and then the empty string reduces to I. So this is SK, which we've already seen is K. And then here's S. It has 5 1s and 3 zeros. And I don't know why I have a semicolon there, but and there's the demonstration that it reduces down to S. So it may seem that like all these 1s are unnecessary because didn't we already have all these S's and K's over here? Like, why did we need these parens around it? Well, we didn't need it when they're by themselves, but if you have like terms that you're trying to apply to each other, like if they're enclosed inside bigger terms, you need these 1s on there because in effect they're giving you your parentheses.
So you just apply the right amount of iotas and then add 1s as necessary to parentheses?
Yeah. Well, no, I mean, it's not always 1s followed by zeros. You can have, depending on how you want to group your terms in a tree, you apply the 1s at the right times in the right sequence. So that's all on there. I have some links, and I also have some example code I wrote in Racket, which is a variant of Scheme. And I wrote I cribbed stuff from Chris Parker's page, and then I tweaked it a little bit. So this defines iota. This translates a string using star for, he uses star for function application and I for iota. And then this jot function uses 1s and zeros. Unfortunately, the jot thing is still broken. I haven't completely fixed that. The iota one works though. And here's our sequence, our rotation that goes around. So I thought I'd define those just for fun. So for example, I is x applied to x. And if we run I, applied to 5, we get 5. We apply x applied to x, which is, that's sk. So if we add another x, that should give us k. And then we can apply that to 1. And then we need another argument 2. Whoop, something's messed up. Okay, so I'll end on a bang. But yeah, I defined plus and times in here, so in curried form, so that you could use them to you could use them along with s. Like you can do things like s applied to plus 3, and then apply that to times 5, and apply that to 4, or something like that. Oh gosh, I can't even get the parentheses right on these things. Anyway, I think that's enough for today. So thank you very much.
All right, thank you very much, Lyle. And for our
So
last
should I crush for time, or are we okay staying?